The title of my talk is Low Rank Approximation and Regression in Input Sparsity Time. So the outline of the talk is as follows. I'll first go over least squares regression, as Petros did. I'll discuss known results, our results. Then I'll do the same thing for low rank approximation, and I'll discuss some preliminary experiments and conclude. So just to recap from Petros' talk, least squares regression, you're given some matrix A, it's n by d, and you're given a column vector B, which is n by 1. And we're going to consider the over-constrained case in this talk. So think of n as being much larger than d. And we're going to consider the approximate version of regression. So we want to find a vector x in R to the d so that the length of ax minus b is at most 1 plus epsilon times the optimal solution to least squares regression, namely the minimum over y of the length of ay minus b. We also allow a tiny probability of failure of the algorithm. The failure probability depends only on the randomness of the algorithm. So for every input, it works with high probability. Now, just a quick comment, why are we looking at the approximate version of regression? There's actually a closed form solution for this problem. So y can be expressed as A transpose A inverse A transpose B. AY is just the projection of B onto the column space of A, so the closest point in the column space of A to B. But computing y exactly takes a lot of time. So order nd squared time, and we're going to shoot for a much better running time. So this is why we have approximation and randomization. Okay, so I'm going to talk about a tool called Subspace Embeddings, which will be sort of at the heart of our result. So let K be order d over epsilon squared. We call this an n by d input matrix. And so this here is just a known result. I'm introducing subspace embeddings. So consider a matrix S, which is K by n. And the entries are just IID normal random variables. 0 mean, and say the variance is 1 over K. Then actually the nice thing about this matrix S is for any fixed d-dimensional subspace, that is the column space of A, suppose I look at S times A times X. Then actually with high probability, for all vectors in the column space, the 2 norm of SAX is equal to within 1 plus epsilon of the 2 norm of AX. So it preserves the 2 norm of an infinite number of vectors, the whole column space. Okay, so you might be wondering, why is this true? I mean, you would think that maybe this only works for a small number of vectors. So there's a very simple proof for when the matrix consists of normal random variables. So we want to show that the length of all vectors in the column space is preserved. We can choose any representation of the matrix that we like, because what we're going to show is that, you know, SAX, the length is 1 plus or minus epsilon the length of AX for all x. So why don't we just choose the representation of A that we like? Let's choose the representation of A so that the columns are orthonormal. So then the nice property of the Gaussian measure is that by rotational invariance, SA itself is a K by D matrix of IID normal random variables. And it's well known what the singular values are of this matrix. They're all between 1 minus epsilon and 1 plus epsilon, provided this K, the dimension, the number of rows of S, is at least d over epsilon squared. So in fact, because of this, you can show that the so you have this property of your matrix SA, and because all the singular values are in this range, this immediately implies that for all x, you have this property that the 2 norm of SAX is about the 2 norm of AX. Okay, so what am I talking about? What does this have to do with regression and the problems that we care about? Well, subspace embeddings sort of give you an immediate solution to regression. So why is that? So recall in the approximate regression problem, we want this x, so that the 2 norm of ax minus b is at most 1 plus epsilon of the optimal solution. So consider the following subspace. It's L. It's spanned by the columns of A together with this vector b. So if A might have been d-dimensional. The column space of A has their d columns. Now L is maybe d plus 1 dimensional. Whatever. We apply our matrix S, and it's a subspace embedding, so it preserves the lengths of vectors of everything in this space L. So for all vectors y, the 2 norm of Sy is about the 2 norm of y. For all vectors y in this space L. So, just look at this regression problem. What do we care about? Well, we care about vectors of the form ax minus b. That's some linear combination of the vectors, the columns of A and B, so it's in this space L. So we have that S times ax minus b, the 2 norm is within 1 plus epsilon of the 2 norm of ax minus b for all vectors x, because it's a subspace embedding. So, okay, why don't we just solve the problem in this reduced dimension? So we compute SA, we compute SB, and now we just solve this problem exactly. And this is a lot easier because S only has d over epsilon squared rows instead of the n rows of A. So you can solve this whole problem in polynomial in d over epsilon time using your favorite least squares regression solver. But it doesn't depend on n anymore, this very large dimension. Okay, so given SA and SB, we can solve regression very quickly. But what am I doing? I mean, because computing SA, it looks like it takes a long time, right? I have this dense matrix of of normal random variables, matrix multiplication, looks like nd squared time. But in fact, a nice paper by Thomas Sarlos shows that S need not be a matrix of IID normals. You can choose S in a more structured way, which allows the matrix product to be computed faster. At the same time, it still gives you a subspace embedding. So these are so-called fast Johnson-Lindenstrauss matrices S. So what does such a matrix S look like? Well, usually it has the following form. It has the form S is P times H times D. Now D is a diagonal matrix with plus minus ones randomly on the diagonal. So it's very easy to multiply a matrix by D. H is the Hadamard transform. So the nice thing about Hadamard transforms, if I have an n by n Hadamard transform, I can compute H times a vector in only n log n time instead of n squared time. And P is just, you compute H times D, and then you just choose a random subset of rows of H times D. So that can be computed very easily. I just take some of the rows that I had. So the point of this is that actually SA can be computed in order nd log n time. So that's nice, right? So now for regression, we can compute SA in nd log n time. We can compute SB, in at most that time. And now we can solve the whole problem in the reduced space in polynomial in the small dimension time. Okay, so to summarize previous work, so work by Sarlos, Drinius, Mahoney, Muthakrishnan, Kane Nelson, and others. Basically, the state of the art was that least squares regression can be solved in nd log d plus poly d over epsilon time. And what we show is that you can solve least squares regression in the leading term is number of non-zero entries of A plus poly d over epsilon time. So why is this useful? A is an n by d matrix. A might be much sparser than nd. In particular, in many practical applications, A might only have n non-zero entries, order n non-zero entries. So this is order n plus poly d over epsilon instead of nd plus poly d over epsilon. Okay. So that's our result, and let me describe how we get it. So we take this subspace embedding route, and we give a better subspace embedding. And so remember, a subspace embedding is a matrix S. We're computing S times A. So we define a k by n matrix S. K is a poly d over epsilon. Think of, again, the number of rows is small. And it's a very simple matrix which has been used in streaming applications and elsewhere. And all it is for each column, I choose a random entry, a random row, and I put a random plus minus 1 on that entry. And I do that independently for each column. So is the matrix clear? It's really, really sparse, right? Each column has a single non-zero entry, which is random plus minus 1. Okay, and the surprising part is that that actually works. So for certain k equal poly d over epsilon, with high probability, you get a subspace embedding. Now, so just a moment on a word about the time complexity. As I said, S is so sparse, SA can be computed in the sparsity of A time, right? Because you just touch each entry of A once. It goes, each entry of A corresponds to a single row of S, and a single column of S, and it just gets hashed to a single row. So SA, since it's so sparse, can be computed quickly. And as I said, once you have a subspace embedding, regression immediately follows. So we get regression from this result. Okay, so why did people miss this? It seems like a simple way of doing subspace embeddings. So usually the argument that you get a subspace embedding works is that you have your column space of A, and you put a net on this space, a very fine net. Like if I have a d-dimensional space, I have, say, exponential and d vectors. And you argue that for all vectors in this space, that the 2 norm is preserved. And since you have a very fine, so now you've reduced the problem to a discrete problem. Like S will preserve the length of all vectors in this net. And then you argue that since the net is sufficiently fine, that actually you preserve the lengths of all vectors in the subspace. That's how all these arguments worked. And in fact, this matrix S that I'm describing as our subspace embedding, if you were to choose an exponential number of vectors that were arbitrary, just, I have some 2 to the d vectors in Rn, then actually this wouldn't work. It works because the vectors come from a subspace of d dimensions. And this is sort of the key thing that is that drives the analysis. So, and actually it all comes back to leverage scores, as Petro has talked about in his talk. So let me give you the intuition why it works. So first of all, you see that to prove this statement, that it's a subspace embedding, we just need to prove it for unit vectors x, because it's a linear map, so it scales. We can choose any representation of A that we like, since we're going to prove this for all vectors in the column space of A. So let's choose the representation for which the columns of A are orthonormal. Okay, so the columns of A are orthonormal. So I have an n by d matrix with orthonormal columns. That means its Frobenius norm is d. Its squared Frobenius norm is d, right? I mean, each column has squared Frobenius norm 1. So now we're going to let a set T be the set of rows in A which have large 2 norm. So in particular, for some parameter beta, which I'll talk about, we look at those rows AI for which the squared 2 norm is at least beta. Well, there can't be too many rows with large square root 2 norm because the overall Frobenius norm is D. So the size of this set T can actually be at most D over beta, just combining these two constraints. So I'm calling the set T the set of large leverage scores. And the really nice thing is that actually, suppose I look at any vector x in R to the D, and I look at the ith coordinate of AX. I look at its magnitude. Okay, well this is just the inner product of the ith row of A with x. By Cauchy-Schwarz, this is at most the 2 norm of the ith row times the 2 norm of x. We're restricting to unit vectors x, so this is at most the 2 norm of the ith row. So what we have is this really nice property of subspaces, which is that a coordinate I is heavy. So we say a coordinate I is heavy if the value AXI is at least root beta. Again, beta is just some parameter. Think of it as 1 over poly D. Then the heavy coordinates are a subset of T, because the value can be at most the 2 norm of AI. And so you need the 2 norm of AI to be at least root beta. So what we have is that as I range over all vectors in the subspace, I can't have every coordinate being large at some point in time or another. It's always going to be the case that there's a fixed set of coordinates which ever get large. And this is sort of the property that's being used for subspaces. This fixed set of coordinates that can ever be large is this set of large leverage scores. Okay. So how do we use this observation? So we call that this is our matrix S, this very sparse matrix. Now just think of it in a different way. The different way is that you can think of randomly hashing the coordinates into k buckets and maintaining the inner product with a sign vector in each bucket. Why is that? Well, each bucket corresponds to one of the rows of this matrix. So let's think of this matrix differently. We have k rows here. Let's think of having k buckets, 1 bucket for each row. And the stuff in the ith bucket is the stuff for which the columns for which the single non-zero entry in that column is I. And so we hash coordinates into k buckets, and in each bucket we maintain the inner product with a random sign vector. That's just a different way of looking at this mapping. Now why do I want to look at it like that? Because when you think of it as hashing, then consider this set T of large leverage scores. If I make my number of rows or my number of buckets k larger than T squared, then actually all of these large leverage scores, the coordinates which could ever be large, get perfectly hashed. Right? I mean, if I have R items that I throw into R squared buckets, with constant probability they all get isolated. And that's the property we use. So if k is at least 10t squared, and t, the size of t, well, it's at most d squared over beta squared, right? It's all those coordinates which could ever be large. So then with constant probability, all the coordinates in t get perfectly hashed by this mapping. Call this event E, which only holds with constant probability. And let's condition on this event E in the remainder of the talk. So in some sense, this is how we deal with the heavy coordinates. More on this in a second. So we're trying to show that the norm of y equals ax, an arbitrary vector in the column space, is preserved. So let's decompose y into the sum of two orthogonal components in the standard basis. So consider y sub t, which is y where we zero out all the coordinates not on this the set t, and we leave the coordinates in the set t alone. And y of n minus t, which is we zero out all the coordinates in t, and we leave the coordinates in n minus t alone. So I'm just writing y like this. And if you look at the 2 norm of sy squared, then just expanding it out, it's the 2 norm of y sub t squared plus the 2 norm of, s times y sub t plus the 2 norm of s times y n minus t squared plus twice the inner product of syt and sy n minus t. And what we're going to do is we're going to bound each of these 3 terms. That's how the analysis will work. So we need to bound syt squared, right? So this is the heavy coordinates in y. Well, event E occurs, right? So all the heavy coordinates get perfectly hashed. So actually we have an isometry. Like the 2 norm of syt squared is actually equal to the 2 norm of yt squared. So we sort of dealt with all the heavy coordinates immediately, given this event E, which we just conditioned on at the beginning. Okay, now we need to bound the 2 norm of sy n minus t. Now the key point is we've removed all the heavy coordinates from y. That's what y n minus t means. So the infinity norm, the maximum coordinate value, is small. And now we can apply this very nice result of Dasgupta, Kumar, and Sarlos, which basically shows that our mapping S works on vectors which have small infinity norm. So the technical statement is that there's some alpha, which again is like 1 over poly d over epsilon. So that if we choose our number of rows k to be sufficiently large, log 1 over delta over epsilon squared, then for mappings of R form S, which are just these hashings and inner products with sign vectors, then for any fixed vector y with infinity norm at most alpha, its 2 norm is preserved by S with very high probability. So, if we set our parameter beta, so we call that T is the set of coordinates which could ever be at least root beta. If we set beta to be order alpha squared, which is 1 over poly d over epsilon, then actually the infinity norm is at most order alpha. And so, y sub n minus t has infinity norm at most order alpha, so we can directly apply this theorem of Dasgupta, Kumar, and Sarlos. So, okay, we bounded the heavy coordinates by perfect hashing. We bounded the light coordinates by appealing to this theorem. So what's left? Yeah, so this is just plugging into this. What's left is to bound the cross term. So we need to bound the inner product of syt and syn minus t. Okay, so yt is, y only has t non-zero coordinates, the heavy coordinates. So syt only has support on t coordinates because it's this hashing. Okay, so now we define a set G in the complement of T to be such that if I'm a coordinate in G, then I collide with one of these heavy elements. So it means that there exists some bucket which contains a heavy element for which I land in the bucket with that heavy element. So in fact, all that matters, so the inner product of syt and syn minus t is actually equal to the inner product of syt and syg. There's no reason to look at coordinates that don't collide with one of the buckets containing a heavy element, because the inner product will be 0 on that coordinate. And by Cauchy-Schwarz, this is at most the 2 norm of syt and the 2 norm of sy sub g. Okay, but we condition on this event E, right, which basically preserved the heavy coordinates. So the 2 norm of S y sub t is equal to the 2 norm of y sub t. We're looking at unit vectors without loss of generality. So this is at most 1. Okay, so now we just need to bound this 2 norm of S y sub g. Well, we look at the coordinates that hash to the same buckets as the heavy coordinates. And the mapping there itself is a random mapping into buckets where in each bucket you maintain the inner product with the sign vector. So we can apply dks again on the restriction of y to coordinates that collide with the heavy coordinates. So we can bound syg, the 2 norm, as 1 plus epsilon of the 2 norm of y sub g, with probability 1 minus delta by dks. And finally, well, what is the 2 norm of y sub g? This is those coordinates that aren't heavy, that collide with the heavy coordinates under the mapping. Well, you can apply Hofting bounds to show that, so all these coordinates are small. Typically, I don't collide with a heavy element if I have enough buckets. So actually, you can bound this by epsilon just by Hofting bounds with high probability. So, so just combining all these things, we get that the probability that this cross term exceeds 2 epsilon is very small, at most 1 minus order delta. And now we can just put it all together because given that this event E of perfect hashing occurs, then for any fixed y with very high probability, we have the following. So this is expansion into cross terms. We said the first term was preserved. The second term preserved up to 1 plus or minus epsilon. The last term is order epsilon. And since y is a unit vector, you can just translate this additive error into relative error. You just go through a simple calculation, and you get that this is 1 plus or minus order epsilon times the 2 norm of y squared. And so that's it. So basically, what we've shown is that for every vector, the 2 norm is preserved with probably 1 minus delta. And now all we do is a standard net argument. We set delta to be 1 over 2 to the d, and we do a standard net argument, which I don't have time to get into. But basically, now it's a subspace embedding, which works for the whole space. So I don't have time to get into some of the other results. Unfortunately, but let me just say what our result is. So this problem of low rank approximation, we can use our same subspace embedding to improve the previous nd log d plus nd log d time algorithm to roughly to sparsity of a time algorithm. And it just follows previous work by plugging in our subspace embedding. We've run some preliminary experiments which are quite promising. Just note, like the dominant term in the time complexity is just S times A, which is just, it takes time, which is number of non-zero entries of A. Now, if you want to compare it to something like Lantro's algorithm, just multiplying a single matrix vector multiplication already takes number of non-zero entries of A time. So, we have some graphs which show that this is very competitive. So let me just conclude that we have the subspace embedding, which works in number of non-zero entries of A plus poly d over epsilon time, gives the same time for regression and the same improvement for low rank approximation. And actually, in Petros' talk, so I didn't mention, you can use the same idea to approximate all the leverage scores in the same amount of time, sparsity plus poly d over epsilon. So that's all. Thank you.